Have you ever wondered if you could see the fundamental building blocks of the universe? I'm talking about the tiny invisible particles that are zipping through you, me, and literally everything around us, every single second. Well, it turns out you can. Let's dive right in.
So take a look at this. What you're seeing isn't a drawing or some kind of special effect. Nope. It's an actual photograph of the trail left behind by a single subatomic particle. A thing so small it's basically invisible by definition. So, how in the world can we capture an image like this? Well, the answer involves a little bit of physics, a whole lot of creative thinking, and an invention that was inspired by a simple, beautiful, natural wonder.
The story starts not in some high-tech, sterile laboratory, but on a windy mountain in Scotland. It's just a perfect example of how sometimes simple curiosity about the world can lead to the most incredible discoveries.
And here's our guy, C.T.R. Wilson. So he's working at an observatory, and he just becomes completely captivated by the rainbows he's seeing in the clouds. But he wasn't just happy to look at them. He had to figure them out. So he goes back to his lab with what sounds like a pretty simple goal, to make his own tiny clouds in a bottle. Okay, so this timeline is where it gets really cool. Wilson starts out just messing around with bottles and a pump, trying to make clouds by suddenly expanding moist air, forcing it to cool and condense. But then he notices something odd. If he zaps the chamber with X-rays, the clouds form way more easily, and that's the aha moment. He figures out the vapor must be condensing on these little charged particles, ions, that the radiation was creating. So what's the next logical step? He points a piece of uranium at his chamber, and bam, he sees these gleaming, thread-like trails. He had just accidentally invented a way to see the footprints of invisible particles.
Wilson was, let's just say, a bit of a perfectionist. The famous physicist Lord Rutherford tells a story about finding Wilson grinding a piston for his device, and then coming back months later to find him still in the same spot, patiently getting it just right. The design he finally presented in 1912 was so perfect that he used that one single instrument for his entire career. When someone asked if it was the original chamber, he just said, "Why, I never made but one."
So, okay, Wilson's device was clearly brilliant. But how does it actually work? How do you get an invisible particle to leave a trail you can see? Well, it all comes down to creating a very specific and very unstable environment. The secret sauce is a state called supersaturation. Just imagine the air is like a sponge that's already soaked, totally full of water. If you try to add even one more drop, water's just going to spill out everywhere, right? Well, supersaturated air is kind of like that, but with alcohol vapor. It's holding way more vapor than it should, and it's just looking for any excuse, the slightest disturbance, to condense that vapor into liquid. And here's the whole process, broken down. First, you get that supersaturated alcohol vapor ready. Then, an invisible, super fast particle zips through it. As it goes, it slams into air molecules, knocking electrons off and leaving a trail of charged ions behind it. And that unstable vapor, it sees those ions and instantly latches onto them, condensing into tiny little droplets all along the path. And the result? A beautiful, visible trail of mist that shows you the exact path that invisible particle took. It's like seeing a tiny jet contrail form inside a jar.
Now, this all might sound like something that requires a priceless museum-quality piece of equipment. But, and this is the best part, you can actually build one of these yourself, using stuff that's incredibly easy to find. So let's look at how modern DIYers have taken Wilson's original idea and run with it.
So there are really two main ways to do this. You've got the expansion chamber, which is what Wilson designed. You pressurize it, then suddenly release that pressure. The air rapidly expands and cools, and for a split second, you get that supersaturated state where you can see tracks. The other, and honestly simpler method, is the diffusion chamber. This one uses a big temperature difference, a warm top and a super cold bottom, to create a constant layer of supersaturation near the base.
And check this out. This is a fantastic example of a homemade expansion chamber. It's literally made from 2 peanut butter jars, some basic plumbing parts you can get anywhere, and a balloon. You use an air pump to inflate the balloon, which shoves liquid up into the main jar, compressing the air. Then you just release the pressure, the liquid drops, the air expands and cools, and boom! For a fraction of a second, you see particle track.
I absolutely love this design. It uses a plumber's friend, a simple rubber drain plunger to act as the piston. You just push it down, let the air saturate, and then let it go. The plunger springs back, creating that super fast expansion. It is just a brilliant, low-tech solution to a really high-tech physics problem.
But if you want to see the action continuously, the diffusion chamber is the way to go.
And this is about as simple as it gets. You just take a jar, stick some felt soaked in alcohol at the top, and flip the whole thing upside down on a block of dry ice. The warm top makes alcohol vapor. It sinks down towards the cold bottom and becomes supersaturated. Just like that, you get a constant, live-action show of the subatomic world.
So if you're thinking about building one, listen up because here are the key tips from people who've done it. You absolutely need an airtight seal. You have to light it from the side with a really strong, focused beam, like from an old slide projector. A black velvet background makes those silvery tracks really pop. Oh, and that temperature difference is everything. Regular ice isn't going to cut it. You need the serious cold you get from dry ice. And maybe most important of all, be patient. It takes a few minutes for everything to stabilize before the magic really starts happening.
Okay, so you've built your chamber. You're seeing these amazing, tiny, wispy trails. What are they? This is where it gets really, really exciting, because just by looking at the shape of these tracks, you can actually figure out what kind of particle made them. It's like particle forensics. Each one leaves a unique signature. The heavy alpha particles, they just bulldoze through the air, leaving these short, thick, straight lines. Then you have the lighter electrons, beta particles. They get bounced around a lot more, so their tracks are thin, long, and often kind of erratic or curved. Super high-energy mesons zip through so fast they leave these perfect, straight, thin lines. And things like gamma or X-rays, they don't leave a direct track, but they knock electrons loose all over the place, creating these random, scattered little wisps.
And this image just shows the difference perfectly. Look at the right side. See those thick, bold lines shooting out from the source? Classic alpha particles. Now, look at the left. All those scattered, misty little bits and pieces, that's the effect of electrons getting knocked around by X-rays. It's a totally different look.
So, just observing the shape of the track is step one. But if you want to do real science, you've got to add one more thing to the mix, a powerful magnetic field. This is how you go from just watching the show to actually taking measurements. Let's go all the way back to that incredible photo from the beginning. The reason that electron is traveling in a perfect circle is because it's inside a magnetic field. That field is constantly pushing on the particle, bending its path. And by measuring the radius of that circle, you can start to calculate some truly mind-blowing things about that one tiny particle. So from that one photo, and knowing how strong the magnet was, physicists figured out the speed of that single electron. It was moving at over 153,000 miles per second. That's more than 82% of the speed of light. I mean, that is just staggering to think about.
And that really gets to the heart of it. As one engineer who built these, Gareth D. Shaw, put it, a chamber without a field is like a yardstick without inch marks. It's interesting to look at, sure, but the magnet is what turns this cool visual into a real precision scientific instrument.
And that is the ultimate payoff. With a magnet, you measure the curve to calculate a particle's energy. And it's pretty simple, actually. The tighter the curve, the less energy it has. If you do this for a ton of particles, you can actually create a graph that physically proves Einstein's theory of relativity. You can see how a particle's mass seems to increase as it gets closer to the speed of light. All of this from a homemade device.
I mean, what an incredible story, right? It all starts with a physicist just looking at a rainbow, and 100 years later, you have hobbyists in their garages using pickle jars and plungers to verify the fundamental laws of the entire cosmos. It's just such a powerful reminder that sometimes the biggest questions can be answered with the simplest tools, as long as you have that spark of curiosity.
The fact is, we are constantly surrounded by this incredible unseen world. A blizzard of particles from outer space, from the Earth itself. The cloud chamber is just one clever way to pull back that curtain. And it just makes you wonder, what else is out there, just waiting for someone to find a simple, clever way to see it?